So in this video, we will be covering how to write and balance redox half reactions. So we generally split up our redox reaction into two separate half reactions. One of them is going to be your oxidation half reaction, and the other one is your reduction half reaction. So your oxidation will have your electrons as products. It produces electrons because whatever is being oxidized is losing those electrons, so you'll see them as your product. See? And then for your reduction, or whatever got reduced, you will see the electrons as your reactants because it's gaining those to form your product. I apologize if you hear the rain in the background. It's kind of loud. But we are going to be balancing redox reactions using something called the half reaction method. So we're going to be using those half reactions we just talked about. And we know that each of these half reactions has electrons in them. It's just they have them on different sides. We are going to use those half reactions, balance them with their atoms, and then balance them with their electrons as well. It's just a process, and I have it listed on the next slide, and we're going to go through that process and apply it on an example. Okay, so the first part of this process is to assign oxidation state. So that's the whole reason we reviewed that, and we practiced a bit on that. I am aware, we didn't practice every single rule in that particular video, but definitely take a look at the little chart that I included on the slides, on that example slide, or just Google redox oxidation number rules, and you'll probably find an even better little table or list. I like that particular little list, that's why I included that one. So if you want to use that one, you can stick to it. After that, we write our half reactions, including our electrons. Balance first the atoms, so by mass we mean the atoms, and then half reactions by charge, so the electrons. So those are the major portions. First the atoms, then the electrons, and then we add it all together. We check everything one last time, and that's basically it for balancing these reactions. Okay, so first we are going to assign oxidation states. So we are given, in this example, we're given solid copper, nitric acid, and we're yielding aqueous copper ions and nitrogen monoxide gas. So in this problem, it is a little bit time consuming because, it doesn't even give you the elements written out, it gives you the names. So it is going to require a little bit on that. It's okay. Like I always say, these examples are the hardest versions of these problems. On the exam, I try to make it a little bit less time consuming by having some shortcuts or having some things already solved out. But anyway, we are going to determine the oxidation numbers for all of these. So we have solid copper, Cu, copper, so each of these are going to be individual. Nitric acid, which is HNO3. So I'm getting these names and symbols. This right here is just the name of an acid, so there's a naming system to those acids. Nitric refers to nitrate ion, which is this part right here, the NO3, and the H in front of it refers to it being an acid. And then solid copper, it's just the element and then solid written after it. Acid is always aqueous, that's why I put the aqueous. So there's a lot of layers of knowledge kind of built in. So that's why I'm just explaining it as I go along. But anyway, we have aqueous copper ions. So that one's easy because it gives us a charge right there. And it tells us that it's aqueous, so super easy. And then nitrogen monoxide. Nitrogen monoxide is a molecular compound which it tells you the prefixes, which tells you how many of each atoms there are. Whenever you only have one atom for the first element, it's implied based off the fact that you don't have to say mono. So just it being nitrogen means there's only one of them, and then monoxide, just one. Gas. Okay, so we have that at the very least. Now we are going to assign our oxidation states. So this would be a good place to have your little rules either like right next to you or on your phone, or you take a picture of them or something, or list it out on a piece of paper or something, so that you can use them to assign oxidation states, because I'm just about to go from like memory. I'm going to explain it, but I'm going to go based off of memory. So copper solid right here is a just atom by itself in its elemental state. This means the oxidation state is 0. Okay. The oxidation state for a monatomic ion like this will be the whatever the charge is. So here the oxidation state is +2. So we have 2 down so far. Next, for each of these compounds, so first we have nitric acid and then we have NO. So for each of these is where you would determine oxidation states for everything, right? So for example, hydrogen and oxygen here are knowns because they have very common oxidation numbers, which we can apply based off of those rules to this situation. Overall, the oxidation numbers for this is going to equal 0. There's 3 oxygens, each of them is -2, so total they're contributing -6. Each hydrogen right here is +1 since it's not bonded to any metals, so it's going to be +1. And then here our unknown is our nitrogen. So here essentially we're solving for x. So, and basically you just want it to equal 0. So in order for all of these numbers to equal 0, it's going to be +5. So the oxidation number for this nitrogen is +5. And like I said, I know I'm going fast for that, but it's review. So just if you need to, pause it, take it slow. Okay, so this one again, it's a compound that's neutral, so it's going to equal 0. Here your known is oxygen. Oxygen has a role associated with it whenever it's in most compounds, it's -2. So we just have one of them, it's -2, so -2. Here our unknown is our nitrogen. So here, in order for this to cancel out, it would just be +2. So we have the individual charges for everything. Okay, so now we can set up and determine what got oxidized and what got reduced. That was the whole point of this, of assigning oxidation numbers. So we have copper solid going to copper ion aqueous, right? And it's starting off with an oxidation number of 0 and it's going to +2. Anytime you're going more positive, you're increasing the oxidation number and you're losing electrons. So you lost 2 electrons in, you have protons equaling electrons whenever something is neutral, such as right here. And whenever you lose electrons, for in this case, it's 2, you're going to have 2 extra, basically 2 protons extra, and no electrons to cancel those out. So it lost 2 electrons. We're not going to focus on that just yet, so let me go ahead and delete that. But we are going to deal with that in a little bit. But what I want you to know is that this was oxidized. So the copper got oxidized. And our second half reaction, which obviously is going to be your reduced half reaction, is this, right? So in this situation, we started off we have hydrogen in one of them, we do not have hydrogen in the other. Don't worry about that. It's going to all work out. What you want to focus on is the one that changed. So I'm going to highlight that for you. Nitrogen went from +5 to +2. Oxygen stayed -2 each individual oxygen. And then hydrogen, you don't see it in the other one, but that's not what we're focusing on. Nitrogen is the one that's changing, and that's the one that's telling us what's going on. So nitrogen here went from +5 to +2. So here it's going from more positive, so a higher oxidation number right here, to a lower oxidation number. That means it got reduced. So we have our half reactions. We know which one got oxidized and which element got reduced. So in our next step, we are going to write out our ox and reduction half reaction. So we know that for oxidation half reaction, the electrons will be on the right, and for reduction, the electrons will be on the left. So I'm going to write them over here to the side. They're basically written out right there, but just so that we are starting fresh, because there is a process to this. So we know we're going to leave space in for our oxidation on the right. So to the right of that, we can write in our electrons, whatever we need. And then for that's our ox, and then for our reduced, it is our HNO3 aqueous. And we know we're going to leave in some space for our electrons, and I'll just kind of leave it open. And we are eventually just forming NO gas. Okay, so we know where everything's going, right? There's going to be electrons to the right of that, and then for reduction, it's the opposite. Okay, so we're done with number 2. Balance your half reactions by mass. A, first balance elements other than hydrogen and oxygen. We fortunately do not have to do any of that. So we have 1 copper right here, 1 copper right there. We're good with that. We have 1 nitrogen right there, 1 nitrogen right there. We're good with that. And then anything hydrogen or oxygen, you will take care of that in the next steps. So we're done with A. And I know that's kind of hard to see, but that's what I'm using. You can zoom in on your slides, hopefully, on the PDF or PowerPoint. And next we are going to add water molecules, liquid water molecules, where O is needed. So I'm going to show you how to do this. So anywhere you have an unbalanced amount of oxygens, you will add waters. So for example, here we have 3 oxygens. We only have 1 right there. So that needs to be balanced. So we're going to balance it using waters. So we need a total of 2 more oxygens. So first I'm going to write out my water, liquid. And then to make that 2, I obviously only have 1 right now, right there. So I'm going to put a coefficient in front of that, just to make this neat. Okay, so far I've balanced my oxygens. And that's really the only spot where you have to. So what's the next rule? Add H plus where H is needed. So we can now see that our hydrogens are not balanced. So we have 1 hydrogen right here, and I have 4 right there. So I need to add hydrogen. I need to add 3 hydrogen plus aqueous. So that is the form you will add your hydrogens in aqueous proton form. So something I didn't mention, but it will come up again, is this is an acidic solution. So I will let you know whether it's acidic or basic, but basically that's your next step. If the reaction is done in a base, you neutralize any protons you have with OH. In this case, we don't have to neutralize, we can just leave it the way it is. We can move on. So next we are going to balance our half reactions by charge. You balance charge by adjusting electrons. So this is where we're going to start adding our electrons in. So in the same red color, I'm going to write on each side what the charge is. So on this side of the reaction, I have a charge of 0. On this side of the reaction, I have a charge of +2. And these are ionic charges, so we are referencing ionic charges in this case. On this side, we have a total plus of +3, a total charge of +3. On this side, we have 0. So anytime you have these charges, these pluses, you are going to balance them out with electrons. So I'm going to balance this out with 2 electrons. And I'm going to balance this side out with 3 electrons. So this is what I have so far, each half reaction. And now we finally put our electrons in. So this was just to show you like where the split is. So I got these charges from these ionic charges right here. Okay, so I had 3 of them right there. That's why I wrote 3. And then I had only 1 right here. That was total +2 on my product side. On this side, everything was neutral, right? There's no charges, that's why it's 0. On this side, neutral, that's why it's 0. Right here is neutral, that's why I didn't contribute anything. So hopefully that kind of helped the coloring. Okay, so now we have taken care of charges. Next, we are going to balance our electrons between the half reactions. So what does this mean? So notice that on one of these half reactions, we have 2 electrons. On the other, we have 3. So that is something we need to balance. So here's what we're going to do. We're going to multiply this entire half reaction by 3, right? Because that's their next common factor. And we're going to multiply this one by 2. So I'm going to go ahead and rewrite everything, but I'm going to show you how this is working, right? We're just foiling everything out. It's just a coefficient. And then right there. And you get the point. But that's what I'm going to rewrite right now. Okay, so I wrote everything out, rewrote everything out. And like I said, all I did was I foiled everything out, rewrote with new coefficients. And now it's looking a lot neater. So our next step is actually going to be to add our half reactions. So we have balance, we have done all of these steps. We are going to add our half reactions and we're going to check everything at the end, double check everything. So when you add these up, all your reactants will go on one side, all your products will go on the other side. So remember, hopefully, that anytime you're adding reactions, in whatever case it is, if you have something that's exactly the same on both sides, it cancels out. So for this case, we have 6 electrons on our products, 6 electrons on our reactants. They cancel out. That was the whole point of making sure that those charges cancel and making sure that these coefficients, match, right? So now we can finally rewrite everything. So I'm going to rewrite that and then come back. Okay, so I rewrote everything and now it's all together as one giant equation. So what we're going to do is just make sure real quick that atoms are balanced and also that charges are balanced. So I have 3 coppers, and I'll just highlight so you can see I have 3 coppers, 3 coppers. I have a total of 2 nitrogens right there, 2 nitrogens right there. I have a total of 2 plus 4, that's 6 oxygens, and also right there. And then I have a total of 8 hydrogens on that side. I have 2 hydrogens right there, 6 right here, that's also 8. So just a real quick check. And then another important part of this, of checking, is checking the overall charge of each side of the equation. So I have 6 protons, which means I have 6 plus or plus 6 charge on this side. On the other side, I have 2 plus coppers. So 3 times 2 plus, that's plus 6. So everything else is neutral. That's why I didn't say anything about those. But everything else, all of this evens out and it's completely balanced. So I know that was a long process. That's why I made this video on its own. This is in acidic conditions, so we didn't have to do anything to these protons. We just kind of went along with the process. In the problem solving session, I will show you how to do the basic solution, but for this, it's basically what we went through anytime you have acidic solutions. So like I said, I know that's a lot of steps, but just take it one step at a time. Make sure to follow the process. I know it's really tiny now, but that's, you saw me take it step by step. And after that, it's just maybe practicing a few more of these problems.